So far, we've seen how to handle, and we've derived a nice formula for what happens if we have a series combination of resistors or if we have a parallel combination of resistors. It turns out, though, that oftentimes you have a combination of resistors which is actually neither. Nonetheless, you can apply a very powerful technique known as the reduction by equivalent elements. So let's take a look at this idea in practice. So we're going to look now at a more complicated circuit, and we're going to handle it by this reduction via equivalent elements. So here's an application of this idea, or an example, if you want to think of it as an example. So I'm going to have an EMF, a battery, strength curly E, and the current will come out of my battery, and it's going to go into what looks like a parallel combination, where on one branch I have a resistance R3, but now on the other branch, instead of having a single resistor, I'm going to have a resistance R1, which will then be in series with a second resistance R2. And then after that series combination of R1 and R2, that's when I'm going to end up now completing my parallel combination, and then I'll bring it back around to the battery and complete the circuit. And the question might be to analyze this circuit and, for instance, to determine the final total current that would flow through this particular combination. Now, to analyze something like this, you realize at first you might think, well, I've got two resistors in parallel. But if you think about it, that's not really what I have here, right? I've got a resistor, but he's not in parallel with any other resistor. He's actually in parallel with a combination of two resistors. So what we can do as a first step in analyzing this circuit is to take these two as a combination and replace them with their equivalent element, because we know mathematically the terminal characteristics of that equivalent element, right, across these terminals here, are mathematically exactly the same as this original combination of resistors. So we would then replace this circuit with a new circuit which I could redraw, which has my EMF, right, and my current flowing out of it, my battery with its two terminals. And now it does go into a nice parallel combination of R3, but R3 now is in parallel with some equivalent resistance. I'll call it REQ. And we know the value then of this REQ. This equivalent resistance, it was completely equivalent to having the sum of my original two resistors. Now that I've reduced this combination to make a single resistor, I now do have a proper valid parallel combination, where now I know that all of the elements here have the same potential or same voltage across them. In this combination, that wasn't true. R2, for instance, does not have the same voltage as R3. But now that I've reduced these two, I have a valid parallel combination, and so now I can reduce this circuit yet again to a yet simpler circuit by taking a parallel combination. So now I can redraw my circuit yet again with my battery, my EMF out here, and my current I flowing across. And now he comes down, and I can replace this unit now with its complete equivalent with the same exact terminal characteristics. That will be some equivalent resistance. It won't be the same as this equivalent resistance, so let me call it REQ prime. That then can complete my circuit. And I know here that REQ prime follows the formula that its inverse is equal to the sum of the inverses of these two which I've put in parallel combination, REQ inverse plus R3 inverse, like so. Or sometimes it's better just to say, well, I know what this equivalent resistance is. It's this combination that you see here, the whole thing inversed. That's the formula I had given you earlier. Now we're basically done, because this is back to our simple circuit where it's just an IR circuit. One resistor hooked up to a battery. We know the answer to this. The current that flows is the EMF divided by the resistance. That's this R prime EQ. And at this point then, it just becomes a matter of substitution to solve the problem, right? I have to divide by R prime EQ. That means multiply by its inverse, which means multiply by this stuff. So if I multiply by this stuff, I have the EMF, of course, is what I'm starting out with, E. I multiplied by the inverse of this, so it's the inverse of the inverse is just the thing back itself. And the thing I'm multiplying by is the inverse of the equivalent, which was R1 plus R2. So that gives me 1 over R1 plus R2. That's this term. And then plus R3 inverse. So plus, since we're using reciprocals, it might look a little neater, 1 over R3. And then that, my friends, is the answer for the current for this particular problem. So you can see the power of successively reducing any combination that is either a valid series or a valid parallel combination. You often can reduce the circuit down to just a simple battery resistor circuit, and you have your final solution. That's not always possible, and in future discussions we'll talk about how to handle the cases for circuits which are so-called irreducible circuits that can't be reduced by this technique.